Hello everyone, welcome to lecture number 5. We already talked about some stuff of time complexity. In this lecture, we learn about more and deep dive into time complexity. So let's start. Big O notation examples. We say a function of n is 30,000 is in the order of 1, which is we write here this is a constant time complexity. Growth rate of 30,000 is constant, that is it is not depend on problem size. So it's called constant time. So in constant time basically there is a loop we run. Let's for loop and which is 1 to 3,000 time. So this loop is did not depend on input size or input, so we call its constant time because this did not depend on input. Constant. We it did not or depend how large the input is, so this is always run 1 to 3,000 time, 30,000 time, whatever the input is. So this is the constant time. Now let's learn about function of n. uh, 30 into n plus 8. This time complexity is this one. We take the worst case which is 30n and we skip the this constant value 30, so the complexity is order of n. Growth rate of 30n plus 8 roughly proportional to growth rate of n. This is linear time. If you talk about this one, then this is the for say user input. We take int n, we take an n is a user input. We use C++ code for seeing and we run a loop 1 to n. So this is depend on n, so this is linear time. This time complexity is order of n. I hope you understand. Let's learn another one. Function of n equal to n square plus 1. This is the worst case from here and we take this one as a time complexity. This is quadratic time. In general, any order of n square function is faster growing than any order of n function. Faster growing means this is slower than this one. This is slower than this one. For large n, order of n square algorithm run a lot slower than order of n algorithm. So let's see of example of order of n square. Let's take user input n, then we run a loop for 1 to n. In between this loop we run another loop 1 to n. So this is the n square order of n square example because we use nested loop. If we use another loop here, then this time complexity will be um, raised to order of n cube. If we use two loops in nested loop, then the time complexity is order of n square. So that's how it's work. I hope you understand. If we visualize the graph, then our doubt should be more clear. Visualize. So this is the function of linear graph and this is the function of quadratic. In number of input is increasing here and runtime. You can see here for such a specific input, the quadratic function is runtime is more lesser than a linear function. But when we increase the number of input, this this one is curve and go raise faster. You can see from here, and this is our cross point. So if we increase the number of input, the linear function is straight same and it goes raised from this way. But in quadratic function, suddenly it curved and instantly raising the runtime. So you can imagine from here, this is faster and this is slower. So now let's go to complexity graph. If you follow this graph, your doubt must be more clear. You can see from here, this is the time complexity, these are time complexity, this is exponential, this also exponential. There is, if we go exponential, then the time complexity is raising. I think you follow the graph. Asymptotic notation, we always calculate O notation. This is the upper bound, the worst case, this is the lower bound, best case, and this is the average case, tight bound. If you explain this, for example, we short a array 7 8, no, shorted not be used here. We find a value from a array 4 1 2. For example, uh, first question is or first problem is find 7. So if we always know that a array indexing start from 0, so this is our indexing 3 4 and 5. So if we search the 7, then we find it at index 0. So this is the best case because we did not search all this value, we just search the first value and find our required 7. If you take 4 or 5, then this is the average case because we have to search half of the array. This is average case, and if we want to find 2, then we must search one by one until we get 2. So we have to search all the index of the array. So this is the worst case, and we always calculate the worst case, which is order of something, let's example n. This is the notation we use. This is the worst case or upper bound, order of notation, asymptotic uppercase. uh, we already discussed about that. If we follow this graph, your doubt must be clear. So this is the best case we find earlier. Average case we have to search from the middle, then the worst case we search all the element of the array. This take more time than this one, and this take more time from this one. So this is the process. I hope you all understand. That's all for today. Thank you everyone.